All right. Good morning, everyone. Welcome to the Sun Nuclear booth. I'm thrilled with this audience and this attendance. We do have a very exciting new product introduction for you. And I would like to introduce Raj Lati, who is one of our program technical managers at Sun Nuclear. This is his project. So we're going to speak directly from the developer himself of what we built and why we built it. We're thrilled to have him, thrilled to have this audience. I turn it over to you, Raj.
Thanks, Dana. So I'm Raj. Thanks for the introduction, Dana. So I'm Raj, one of the technical product managers at Sun. And today we'll talk about, the how and why we made the daily QA4. One question which you're probably all wondering is why not just keep selling the daily QA3? I mean, it measures your output, measures your flatness, your symmetry. What more could you really want from a daily QA device? Well, the thing is, right, if you look at any traditional C-ARM or Bohr-based Linux system, you do have a lot of moving parts. It's pretty complex. You could have had mechanical slop in the chain, the drive screw, you could have loose inclinometers, walkout from gantry rotation, whether from installation tolerance or just wear and tear over time. And this all results in, in an error between your RT and your imaging isocenter, which of course leads to, inaccuracies in your beam delivery. So as a user, I would want to know this every day. The problem with how we currently measure is that you have an array, which you can't image. It usually does output, symmetry, flatness, just like the daily QA3. There's no isocenter information, and you can't take any profiles other than the 20 by 20, so no small field profiles. And then after that, you take an imaging phantom like an isofan, which does not measure radiation, no profiles, just measures offset. So what you're left with, is that you're measuring two different subsystems. I'm using two different phantoms with two different setups, and you're not going to get one integrated answer. So rather than evolving the daily QA3, we said let's just begin with a blank page, and it's actually one of the original napkin drawings we made when we made this concept. Is that we have to measure isocenter in 3D. Not just to locate it where it is, but also how large is it. We wanted to measure profiles more than just your 20 by 20, so we needed a high resolution array. Of course, we wanted to measure energy, so we said, let's just integrate our wedges inside. But most importantly, we wanted to image it, because that's the whole purpose of the end-to-end test. So we had to reduce the metal inside so we could reduce the artifacts. At the same time, we had to shield the electronics just from the imaging dose. Of course, there's inherent, limitations to an array. For example, you can't do any EPID QA position accuracy. You can't do any gantry angle accuracy. So we thought, let's put some markers inside and make it a multi-met Winston-Lutz phantom as well. With all these features inside, now we had to make it easy to use as well. So what you have here is just an overview of how our requirements, our wants, translated into real features on the device. So the measurement of isocenter in 3D, we have two vertical detector arrays on the sides of the device, in addition to the horizontal array. It's got 2.5 millimeter resolution, so it's got twice that of the IC profiler, so we could measure profiles from 2 centimeters to 20 centimeters. We want to measure energy. We wanted to look at area under the curve. So now we have attenuation on the diagonal array. Onboard imaging QA, right? EPID QA. That was done via introducing markers into the device. Unlike the multi-met Winston-Lutz, there's vertical separation of 4 centimeters in the daily QA4. When it comes to ease of use, I think this was a question we got a couple of days ago. It's indexable. So you have your repeatability, your reproducibility. And because the software runs, I have a picture of this later, because the software runs in trigger mode, it knows when to transition from one measurement to the next. So you really don't have to interact with the software at all. Yeah, I just wanted to spend a little time highlighting the features. Here's an example of the vertical detector plane. It also has 2.5 millimeter resolution. It can do a field size up to 2.75 centimeter. There's one on the left and right side, and then the horizontal array. You can see the primary axis, and you can see the diagonal axis. Because we wanted a diode, a CAX diode, right at isocenter, our ion chambers are actually split into 4 microchambers within a 5x5 ROI. You may have noticed that there's some crevices on the top of the device. That was to make it sensitive to SGRT, which you can use for your reposition test as well.
So,
One cool thing which we did with the light field detectors, which you can see at the corners of the device, is that usually there's just an ROI, a painted line, and it's a pass-fail result. It's really hard to quantify. So here with this, if the light,
song and dance, I'll hit and record.
when you see the light
I will
disappear,
come
you
up
can
and
tell if
introduce
it's
you.
plus
Andres,
minus half
schon
millimeter,
wel.
plus
Schon
minus
wel.
1, or plus minus 2 millimeters. So at least you can quantify in the software as well where the light field is. It's got crosshairs all over the place to help in alignment. And then for laser QA, it's got your traditional laser QA. If it's within the 2 black lines, it's plus minus 1 millimeter. If it's on the line, it's plus minus 2 millimeters. And lastly, wanted to talk about the software automation. Of course, because now you can do a 4-angle or an 8-angle gantry test. It's a lot of clicking. Now we have automation mode because it's running in trigger mode. It knows when the beam's off and when it shuts off, when it's on and when it shuts off. It'll automatically transition to the next measurement. So if you have an RT plan running in parallel, you're not touching the software. You just have to press play once at the beginning, and then you let it work its magic. I promised to keep this short and sweet because I wanted to hand it over to our next speaker, but I appreciate everyone listening. And
Wonderful. Thank you, Raj. Are there any questions from the audience before we turn it over? They might be answered by Dr. Barbies. Any questions? Yes, we have one. Here, hang on.
Vertical side. On the side, what's the diode or chambers? What do you have on the side? And what is the resolution?
2.5 millimeters, and they're all diodes.
All right, beautiful. Thank you.